NATO G5511 Science for Peace and Security Program Multi-Year Project Cyber Defense and Intelligent Logistics Systems. Participants: Technical University of Sofia in Bulgaria, Kraków National University of Radio Electronics in Ukraine, ECAM EPMI in Paris, France, and University of Jyväskylä, Finland. In today's world, most companies have either entirely digitized their business processes or are going through a digital transformation, and automation and robotization is at the core of physical process optimizations. But this digitalization has been opening an ever wider front for cyber attacks on companies, both private and state-owned. The rapid advancement in AI-based solutions for the industry has specifically put what is known as intelligent cyber-physical systems in the focus of the cybersecurity research, as they are unavoidable assets of the Industry 4.0 facilities. The general goal of this project is the development of a proof-of-concept cyber defense immune system, capable of protecting the intelligent AI-based control systems for few different Industry 4.0 logistic installations. This is to be achieved using a digital vaccine against one of the potential types of cyber attacks on intelligent systems, data poisoning. The specific objectives of the project include the development of a system architecture and algorithms providing real-time cyber defense decision-making in supply chains and logistics equipment management. The resulting intelligent immune system will be capable of protecting the AI-based control system incorporated in modern cyber-physical systems. In this intelligent immune system, an artificial attacker or a generator is trained to generate well-disguised and continuously improved attacks by creating fake data as an input to an AI system. An artificial defender, on the other hand, or a discriminator, is trained to distinguish between fake and real inputs coming to the AI system and constantly improving the ability to repel the attacks. Some of the specific goals of the project also include an upgrade of the so-called pilot demonstrator. The pilot demonstrator for this multi-year project comprises of 3 different logistic systems, capable of operating under real-life conditions. Logistic systems are at the core of every industry, and are often part of the critical infrastructure which is targeted by cyber attacks. Both Technical University Sofia and ECAM EPMI France have various industrial installations as part of their experimental facilities, which can be used for the purposes of this project. Logistic System 1 is an automated storage and retrieval system, available at the experimental facility of Technical University Sofia, and respectively, it was upgraded under this project with new industrial-grade automation and SCADA capabilities. The automated and storage retrieval systems are a standard equipment for many warehouses and are essential for the efficiency and preciseness of delivery. Logistic System 2 is an inter-row conveyor, also available at the experimental facility of the Technical University of Sofia, and again upgraded to the latest industrial automation standards under this project. The inter-row conveyor installation was chosen because it can be set up in a way to simulate an airport luggage transportation scenario. The third pilot demonstrator is a pharmaceutical production and packaging line available at the laboratory of ECAM EPMI France, which also can easily be seen as a target for a potential cyber attack. The third pilot demonstrator is a real-life industrial system available at ECAM EPMI France. The automated industrial installation is used for production and packaging of pharmaceutical products, and it is equipped with several workstations, including a supervision, pill production, and pill packaging stations. For the realization of a cybersecurity platform, the industrial production system is extended in order to integrate some smart technologies and connected devices in order to obtain the Industry 4.0 dimension. Particularly, a new workstation with an artificial vision system is integrated for the quality control of the tablets produced by the production system. And a second developed part represents the computer and information network, used to connect and control the entire industrial system. The cyber attack and security platform is now ready to be used for new research and development and the execution of various experiments. It can be set up to simulate 2 different kinds of cyber attacks. The first kind is associated with attacks targeting or facilitated by the exploitation of the network infrastructure and the underlying protocols. For example, the industrial firewall protecting the network, or the topology of the network itself, which uses redundancy of some equipment for better security. The second kind of attacks to be considered as experimental options concern the physical part of the system, where various sets of sensors for detecting anomalies can be added for best protection of the actuators. For example, detection of anomalies in the conveyor speed or other parameters, as such anomalies can be symptoms to attacks. In addition, the platform is open source, allowing the possibility to develop and implement specific intelligent algorithms as an additional security layer for the industrial system. We have chosen to focus this research on computer vision AI systems using convolutional neural networks for the classification and detection or tracking of objects, as this is one of the areas where AI has most advanced in recent years and gives a particularly wide field for control solutions in industrial environment. For example, a luggage scanner at an airport uses X-ray imaging to get results on the contents of a passenger's bag. Or, in an entirely industrial environment, a quality control solution may use ultrasound, X-rays, neutrons, thermal sensing, or some other non-destructive inspection method to acquire data on the inspected item. An intelligent control layer for such a system can be deceived by it being provided with false data, which can change the outcome of the decision-making process. In our simplified airport luggage transportation example, we can assume a load passing through the conveyor either containing a threat, which we will symbolically refer to as a bomb, or not containing a threat, or a dangerous substance, which we will be referring to as a normal or safe state. We are assuming the following two scenarios. First, a malicious party may be wanting to trick the system to falsely recognize a load not containing a bomb as a bomb, and thus invoking shutdown, panic, or generally trying to disturb the normal operations. Or maybe the malicious party wants to pass the dangerous substance, or the bomb, through the system undetected, and thus classifying a dangerous load as normal or safe. Similar scenarios can be constructed for the pharmaceutical line and the automated storage and retrieval system, where an adversary might want to scramble the load addresses, or destinations, of the loads, or trick the packaging line into packaging empty containers with no medicine in them. The possibilities for solving havoc are endless if a control solution's decision-making can be manipulated. All three logistics systems include an intelligent computer vision-based decision-making process, which has to be trained to do the designated job. For the conveyor, that is the detection of a dangerous crate. For the automated storage and retrieval system, the camera should monitor the contents of the crate and classify the load type, whereas the pharmaceutical production line uses cameras to monitor the packaging and container labeling processes. All these intelligent systems use some convolutional neural network architecture to do the respective classification or detection and tracking job. Convolutional neural networks require a lot of images to be trained, thus training sets are obtained using the cameras of the respective systems, while making sure that a good variety of lighting conditions, backgrounds, viewing angles, and other factors are accounted for where necessary. As we previously stated, the control solutions are based on different convolutional networks and are either doing classification or detection. We are doing this to test the digital vaccine concept on a wider range of solutions. The conveyor dataset, for example, consists of over 8,000 images of crates with different type and amounts of load. The images are labeled and can be used for training both the object detection and the generative adversarial network. The control layer architecture we choose for the conveyor system is an efficient detection network, used for detecting and tracking the crates and potential dangerous items in them. After the images were labeled, the systems were trained on several high-performance NVIDIA GPUs, using transfer learning from an existing pre-trained model of the efficient DET V1. The resulting model is then implemented in the experimental setup. All three logistics systems use industrial-grade automation hardware and are generally controlled using SCADA solutions. The cameras which are being used may or may not be part of the industrial network, but in all cases the video data is fed into a separate intelligent control layer, usually built on top of the SCADA using OPC or some other communication protocol to convey the decisions made by it. The interroll conveyor is a good example of how we have set up the experimental part of the project. It uses 3 touchscreen HMI panels at various locations as well as a central computer-based operation station running SCADA software which allows the monitoring and, if necessary, a manual diversion of crates. Otherwise, crates are diverted to a specific path based on the barcodes they have. The intelligent control system monitors the video feed over RTSP protocol in a Python environment. It uses the OPC protocol to read optical sensor values, which are then used as triggers along the path of the crate. After a decision-making process, again using the OPC protocol, it either overrides the crate path and diverts it of its barcode-generated path, if it's marked as a dangerous crate, or it is left to pass unaffected through the system. All three logistic systems use a similar environment. In order to protect the intelligent control layers from potential data poisoning attack, they need to be vaccinated using an adversarially generated augmentation to the training set, which can be acquired through generative adversarial network training. Generally speaking, the adequacy of the experimental results interoperability when talking about computer vision neural networks is highly influenced by the quality and the size of the training datasets. The dataset generation process is an ongoing effort for all three logistic systems within the project. And although it is of significant volume and enough for the needs of the control layers, it is still insufficient for working on a new generative adversarial network architecture necessary for the reinforcement of the operational classifiers in the control layers. Therefore, the generative adversarial network research part of this project is done using proven high-quality and high-volume datasets, such as the MNIST. Adversarial training is based on selective sampling, or selection of the most informative or representative instances, reflecting personal features of the decision-making. Various studies prove that the most informative data samples lie close to the decision boundary. Knowledge of samples populating decision space close to the decision boundary is primarily used for learning more accurate classification models. And so we divide the experiments into groups. The first one corresponds to the development of the new generative adversarial network architecture, applicable for the cloning and the security tasks. The second group aims at validating the methods for adversarial-driven selective sampling based on decision boundary identification, running detection, selection, and generation of samples populating regions close to decision boundaries of pre-trained classifiers. Boundary samples are used for cognitive cloning simulations and decision-making behavior modeling. The decision about the affiliation of each data sample to the boundary subset is made based on the confusion of the classifier. The higher the confusion, the higher is the probability of the affiliation. The task is to partition the obtained decision space into 100 more specific classes, representing 100 neighboring areas of digits written similar to one another. To decide on the configuration of the confusion classifier, responsible for the class specification, we experiment with 6 different activation functions and 2 different confusion functions. The most promising generative adversarial network architectures derived from this approach are then trained using the limited dataset produced from the logistic systems, in order to generate adversarial examples, which are then used as augmentation to the training sets for the operational control layer classifiers. The results and accomplishments of this project include the implementation of the pilot demonstrator and the generation of the training data and running of the attack scenarios. The training and testing of the modules of the intrusion detection and prevention system using datasets collected during real-life logistic operations, realized under the pilot demonstrator systems. The implementation of an attack impact estimators for pilot scenarios. The development of a cyber attack and security simulator platform and a simulation tool for evaluation of cyber attacks, specifically for the pharmaceutical line at ECAM FME. The training and implementation of the developed immune system. The training of a detection model for the artificial immune system based on adversarial reinforcement learning. Realization of trained hybrid models for early detection in real-time mode of cyber attacks in logistic systems. The realization of Go reinforcement learning in cybersecurity simulation when stochastic elements and incomplete information is used. Modeling an adversarial game where a number of reinforcement learning algorithms are pitted against each other as the defender and the attacker in a simulation of an adversarial game with partially observable states and incomplete information. Simulation of adversarial cybersecurity games with artificial vaccination where 2 software agents, a defender agent and an attacker agent, have the goal to win as many games as possible. The attacker has the goal of hacking the cyber-physical system, and the defender has the goal to detect the attack. Testing the performance of the different reinforcement learning techniques, and finally, piloting an adaptive reconfiguration of a logistics system under suspected cyber attack.